Okay, so we previously showed the Kakutani's fixed point theorem, and in this new episode, we will use that theorem to prove the existence of Nash equilibrium. Right? So, so essentially, the best response correspondence is just the correspondence F uh, that we mentioned previously, right, in the previous episode, and the action profile is just the set X, right? Those are just the analogs that we discussed. Okay, so before that, so let's just write down the title for today. Okay. Existence of Nash equilibrium. Okay. So before that, let's first introduce some properties for the preference relation. Right? And we start from the preference relation, then we go to the utilities that we use, right, in the proof. Okay. Some properties for the preference relation. Okay, so the first is that whenever we are saying the preference relation or the weakly preferred, this notation is continuous. Okay, we say that what we mean is that if for sequences AK and BK, okay, with limit AK equals to A as K goes to infinity, okay, and the limit of BK goes to B as K goes to infinity as well, okay, such that AK is weakly preferred than BK. Okay, if we have those above true, then we have A is weakly preferred than B. Okay. All right. So that's the first property for the preference relation that we're going to use. So the second one is that so the weakly preferred relation on a real Rn, it is quasi-concave. Okay. So we say that a preference relation is quasi-concave if for any let's say for any subset B of Rn, okay, so the set A as a subset of as an element in Rn such that A is weakly preferred than B, okay. So we collect all those A's and the set A here, this set including all those A's. So this set is convex. So in this case, we mean that the preference relation on Rn is quasi-concave. Okay, so those are two pretty important properties that we use to establish the conditions that we're going to need in the Kakutani's fixed point theorem, right, to show the existence of Nash equilibrium. Okay, so with those conditions, then we can actually to begin the proof of the Nash equilibrium, right? Okay. Existence of Nash equilibrium. Okay. All right. So a strategic game or a simultaneous move game, which is a tuple of n and the action profile, and preference relation, okay, for player I. So this has a Nash equilibrium, or this is called the pure strategy Nash equilibrium, right? So later we'll discuss the definition for the pure strategy. Okay, so it has a Nash equilibrium if for all player I in set N. Okay, so if so we have those analogous conditions as we did for the proof of for the conditions in the Kakutani's fixed 4.3, right? So the first one is that the action profile for player I, AI, this set is non-empty, so it has a non-empty action space, and it has to be compact and convex. So it's a non-empty, compact, and convex subset, okay, of Rn, okay, of an Euclidean space. Right? Okay, so that's the first condition, and the second one is that the preference relation for player I is continuous, and it is quasi-concave. Okay. So it means, as we mentioned, the quasi-concavity simply means that the subset which is which is higher than, or which is weakly preferred than some level, that set is convex, right? So that's the quasi-concavity for a preference relation. So it's quasi-concave on AI, right? Then we can use this preference relation to construct the correspondence that we're going to use in the Kakutani's fixed point theorem, right? Okay, so before that, let's define the correspondence that we're going to use, right? So because we're doing the equilibrium, so we're using the best response correspondence, right? So BI is a best response correspondence of player I, okay? So if BI A minus I is such that, so it's a set of those little AIs, okay, such that those AIs are the best response, right? So the meaning of best response is just the given the other player's actions, then if the player I is playing this AI, then this gives the a weakly higher utility for this player I, right? So that's for, and this has to be true for all the AIs from the action space, right? So rigorously, it means that A minus I AI, so this gives, or this is weakly preferred, then A minus I AI prime, right? So this is true for all AI prime, okay, in AI. Okay, so that's the best response correspondence that we're going to use in the proof of the Nash equilibrium, right? Okay, now let's from the begin the proof. Okay, so we define this B, okay, so this correspondence from A to A, okay, so A is just the outcome, or this is the action profile from all the players. This is the biggest set for the actions, right? So where this BA, okay, with some typical element from A, space A, so this BA is just the Cartesian product for the i's from n and bi given a minus I, right? So this means that so if we input some a into this correspondence, then what we get is the product of all those sets, right? Because each correspondence outputs a set, so the Cartesian product of all those sets, and given the actions from all the other players, a minus I, right? So intuitively, this means that we put everyone's best response into this, right? Into this correspondence, and because the dimension of the input and output, they coincide, right? So they match, surprisingly. So this is because that each one is affecting the other one's decisions, right? So if we fix all the other players' actions, then we plus one. So this exactly, this is the number of, or this is the cardinality of the set of this of the set from the output of the correspondence, right? So that's the exactly symmetric for all the players. So we can always have the same dimensions with the inputs and the outputs here, right, for the B. Okay, so that's the definition for this B. Okay. So later we'll see some examples of that. Okay. So first we note that, okay, so because A is just the Cartesian product of all the AIs, right? So I en for all the i's. So this is also non-empty, okay, and is compact and is convex, right? So for all the i's in N, okay, A minus I is an element of the Cartesian product of the AJ's. So J, okay, J is an element from N, but without player I, okay? So that's the meaning of A minus I, right? We have already defined that previously. So now we want to show, what we want to show is that this BI, given A minus I, so this set is a convex set, okay? So we want to show BI A minus I is convex, right? Okay, so we consider any elements x and y, those two elements in the set BI given A minus I, okay, such that so because those are the elements in the best response correspondence, right? So we must have that either x or y, they're giving the higher utility than the other actions, right? So A minus I, x, so this is weakly preferred, then A minus I, AI prime, right? And this has to be true for all the AI primes in AI, okay? And A minus I, y is weakly preferred, then A minus I, AI prime. So x and y, those are pretty the same thing. Okay, just copy and paste. So given this preference relation with quasi-concavity, right? So given quasi-concave preference relation, so for for all AI primes in AI, okay, then the set including the A's from Rn, okay, such that A is weakly preferred, then the action profile with A minus I and AI prime, okay, is convex, okay. All right. So this is what we have, right? And then for any alpha between 0 and 1, since alpha A minus 1 plus 1 minus alpha A minus I equals to A minus I, okay? And we also have that A minus I alpha x plus 1 minus alpha y is weakly preferred, then A minus I AI prime, this X profile, okay? So this outcome gives weakly higher utility than the other one. So, okay, A minus I of X plus 1 minus alpha y, okay? So this has to be an element of the outcome set of the best response correspondence BI for the player I, given A minus I, right? So from here, okay, let's have some notes. All right. Okay. So from here to this step, so the intuition is that because it's better than all the other actions, right? So it has to be the best response, right? For all those actions, and okay, and this is similar for all the other dimensions, right? So similar for all other dimensions, okay? So therefore, for all the A from the action profile A, then this BA is convex, right? Because we have already proved the dimension for player I, and this is also true. It's also symmetric for all the other players, right? Okay, and this is true because the midpoint or the convex combination is still inside, so we have this convexity, right? Okay. Okay, now this is the first part of the proof. So from here, then we have completed this proof from a quasi-concave preference relation to the convexity of the B, right? So B, which is a best risk correspondence. So this is the first important part of the construction of this existence. Right? Okay, so the second part is is that we're going to use the continuity of the preference relation to show the closeness of the graph of the correspondence, right? So, okay, so that's the first part. Okay, and then we use, so this preference relations, continuity, okay, to prove the closeness of the graph of correspondence. Okay. So basically, whenever we're talking about the continuity, we're going to prove by the limits, right? The sequences and the limits. Okay, so we first consider AK and BK, okay, those two sequences, such that BK is an element of the set for the output of the best response correspondence given AK. Okay, so also, and the limit of AK equals to A given when K is approaching to the infinity, and the limit of BK is B, right? Okay, those are pretty standard. Okay, so for all the i's from N, BIK, okay, is an element of BA minus IK, okay? All right, since this is the best response correspondence, right? So what we have is that A minus IK, BIK, okay? So this is weakly preferred than A minus IK, AI prime, right? And this has to be true for all the AI primes from outcome A, right? So by the continuity of the preference relation, right? By the continuity of this. So for any AI prime in AI, which is fixed, right? We have that A minus I, BI is weakly preferred than A minus I, AI prime, right? So then what we have is that BI is an element of the best response correspondence, BI, given A minus I, right? Okay, so similarly, for all the other players, others, okay, and it's true for all the others, which is symmetric, and then what we have finally is that B together, so this factor B is an element of the best response correspondence of B given A, this vector of the whole action profile, right? So now we have proved the closed graph, right? Okay. So that the B has a closed graph. Okay. Then by the Kakutanis fixed point theorem, okay, there exists a fixed point theorem, a fixed point, right? So finally, by Kakutanis, there exists A star, okay, which is in the equilibrium, right, which is called the Nash equilibrium. So A star, okay, which is an element of the outcome set of the best response correspondence B, and the input is exactly again this A star, right? So that's the most beautiful part of this this proof or this result, right? So it means that everyone's best response is also others' best response, right? So namely their best actions. Right? Okay, so Nash equilibrium exists under the conditions that we mentioned, right? Okay, but we notice that actually those conditions are not easily satisfied, right? So for example, in the finite action space, sometimes the pure strategy Nash equilibrium doesn't exist. Right? and also if those preference relations are not continuous, and the existence might not exist, right? Again, so the fixed point doesn't exist again. So since the action sets are discrete, and later we'll show an extension, or is essentially another game which is using the mixed strategy instead of the pure strategy, right? So we will have the mixed strategy Nash equilibrium, and we'll show that for the finite game using the mixed strategy Nash equilibrium, do the mixed strategies, and there will always exist a mixed strategy Nash equilibrium. Right? So, and in that case, the conditions for the existence of Nash equilibrium will be less, right? So we'll much easier to have the existence of the mixed strategy Nash equilibrium in that case. Okay, but this is the starting point for us to see the fundamentals of those proofs. Okay, using the Kakutanis fixed point theorem for the existence of Nash equilibrium. Okay.